Okay, so the next problem we're going to look at is going to be problem 623. This is a shearing mechanism, as we can see in the diagram here. And what we want to do is we want to use the relative velocity method to determine the linear velocity of the blade as the crank rotates clockwise. So it's going to be going in this direction, clockwise at 100 RPM. So the crank is here, the blade is here. Okay, so we're going to have a crank slider mechanism. Okay. So as we look here, what I want to do is we're gonna sketch out the diagram first, and then we're gonna go over to AutoCAD, and we'll kind of talk our process through and kind of make sense of the information that we have in the process that we're gonna do. So this is problem 623. Okay. And what we are given in this problem is just that our crank is rotating at 100 RPMs and it's going clockwise. So that's really all the information that we're given. So all I want to do here now is just sketch our kinematic diagram before we translate it over to AutoCAD to scale, just to kind of make sure that we're, on the same track and we know what we're looking at, and we can give some things some labels and such. So I'm going to start by using the center, or where the crank is connected to the frame. Okay, so that's going to be the center of rotation there, and our crank is going to be that member. So this is the center of rotation for that crank, and then our crank is going to go out here. We know that our crank is 0.75 inches long and at a 40 degree angle to horizontal. Again, we'll be drawing that to scale in AutoCAD. Then what we need to do is represent our blade, which is constrained to only going vertical. Okay, so it's going to be represented by a slider, and that slider is going to be offset by a 1/2 inch. Okay, so I'm just going to kind of go out here, and it'll be down here-ish, and we're going to show a slider, and that slider is constrained to a vertical direction. So we're going to show then the frame that it can only go up and down here. And then our link is going to connect these two. Now I know my scale isn't great, but this is just a sketch. It's just a sketch. Okay. So now that I have the elements in place here in simplified kinematic diagram mode, then what I'm going to do here now is I'm going to label. So my frame is number 1. My crank is going to be number 2. My connecting rod 3. And that blade or that slider is going to be number 4. Okay. Then as far as the joint labels, this is going to be A. B is going to be at the end of link number 2. C is going to be the center of my slider. And then I'm going to sneak D in like right there. That's going to be between our slider and our frame, where it's constrained to vertical motion only. Okay. So this is going to be the diagram that we create. Now, once we have our diagram created, and this is just for kind of talking through the process, okay? So we'll go over to AutoCAD in a little bit. We want to show that this crank is rotating clockwise at 100 RPM. So we are going to show this in this direction. This is going to be our, where should I put this? W2, and it's going to be equal to 100 RPMs, okay? Now I call it W2 because it is the crank rotating at 100 RPMs, and that is identified as link number 2, so W2, okay? Questions so far? Does that all make sense as far as kinematic diagram stuff? Okay. Now, once we have our diagram created, so first things first, we're going to create our diagram in AutoCAD, right? We're going to create it in AutoCAD. And it's going to be to scale, so we can use that for orientations. Then we know that we need to find the straight line velocity, how fast our slider is going to go. So if we look at this point in time and in the orientation that we're in, if we're going to be pulling this up in a clockwise direction, we would anticipate that the direction of the blade is going up at this time as well. Would you agree? And this would be designated as the velocity of point C. So velocity C right there. And this is what we want to find. Okay, we want to find the velocity C. What is its magnitude? How fast is it going up when our crank is going in a clockwise direction at this moment in time at 100 RPMs? Okay. Now, as we know, we're going to use the relative velocity method because link number 2 is not directly connected to that slider or that blade. It dictates the motion, and the blade is going to move relative to link number 2, but they're not directly connected. So we need to use that relative velocity equation in order to solve this. And as we know, the generic form is going to be the velocity of our unknown. It's going to be equal to the velocity of the known plus vectorially the velocity of the known relative to, I'm sorry, let me get that right, unknown relative to known. Because the unknown is dependent or relative to. Okay. So our unknown velocity is going to be velocity C. That's what we're trying to find in our problem. It's going to be equal to our known. Now, although we don't know the magnitude yet, we will calculate that in a little bit. We know everything about link number 2, okay? Since this is going in a counterclockwise direction, we're anticipating that the straight line velocity of that point B, velocity of B, is going to be perpendicular to the radius back to its center of rotation in the direction of rotation. So it's going to be going up and to the right. So we know direction right now, and we will be able to calculate its magnitude. So it will be fully known. And we'll use that equation of V is equal to WR. Okay, so we'll be able to do that. So that'll be our known quantity, plus vectorially the velocity of C relative to B, which will be the velocity perpendicular to that link connecting B and C. Everybody see that? So this is the velocity of C relative to B. Okay. So as we look down here, I always like to identify my knowns and my unknowns. So we don't know the magnitude of C, but we do know its direction. Okay. And it's going to be along that line, that vertical line of travel for that slider. We will be finding the magnitude of B in our very next step, and we do know its direction to be perpendicular to its radius back to the center of rotation. And then lastly, we don't know the magnitude of C relative to B, but we do know its direction to be perpendicular to the link connecting B and C. Okay. So before we go over to AutoCAD and draw our diagram, let's find the magnitude of velocity of B. This is going to be our step number 3. So we know that our base equation relating rotational velocity or angular velocity to straight line velocity of any point on that same link is equal to V is equal to W times R. Okay. Now we want to find the straight line velocity magnitude for point B. And since point B is at the end of link number 2, which we know the rotational speed for, this is going to be W2. And then the radius is going to be 2 point B. And that's going to be the radius from the center of rotation to B, which we know to be 0.75 from our problem. Okay. So now what we want to do is we want to input our value. So we know this to be 0.75, and we know the rotational speed is 100 RPMs, right? But we know we can't use RPMs in this equation. We need to change it to radians per second. So I'm just going to do that work over on the side here. We're going to take 100 revolutions per minute up, down, remember. We know that 1 revolution is equal to 2 pi radians. Okay, revolutions cancel. And then we've got 1 minute on the bottom. We're going to put it on the top here so it cancels, is equal to 60 seconds. So our W2, what do we get for this value? So multiply across the top, divide by the bottom. Yep, 10.47. I got that same thing, Steve and Logan and David. Awesome. You guys are quick. Okay, and that's going to be radians per second. So this value right here is what we're going to use over here. So this is going to be equal to 10.47 radians per second. Make sure you put your units in, times that radius. And again, that's coming from our diagram right here. Our crank is 0.75 inches long. Inches. So now our velocity of B is going to be 0.75. So I get 7.853. And that's going to be inches per second. So I went to the third decimal place. Anybody get the, oh, it looks like Lars, did you get the same thing? Or was that for the other one? Maybe it was for the other one. Just verify that you get that same number, 10.47, 0.75 times. Oh, so yeah, 7.853. Yep, okay. And again, little clouder on this one. This is not a final answer, but if we look back at our answer key, and this was what I was referring to earlier. Oopsie. If we go back to our module 4 and we go to assignment number 4, we go to problem answers and we go to 23, 7.854. Okay, we got 853 inches per second is our number. So we're going to continue with the 853. But we know that we're on the right track to keep going. And it is a good idea to verify that before we move on. Oh, I see, Logan, you have a question. Why are we using 0.75? So 0.75 inches is the radius from the center of rotation to point B. Okay, and this length of link number 2 is 0.75. That's why. So that's the radius of rotation. Okay. All right. Okay, so now that we have the magnitude of B, we are ready to go back to AutoCAD, all right? And we are going to draw our kinematic diagram first, and then we're going to, get started on our vector equation. So let's go over to AutoCAD. I have already created my diagram for 623. I'm going to give you time to do that very same thing. And I'm going to pause the video for a little bit, and then when everybody's ready, we'll resume. Okay, so we do have our diagram here. Feel free to compare yours to mine. I did add in my dimensions for verification only. As you know, I like to do this just to be sure that everything matches before moving on, because orientation is super important, because I'm going to use the orientations here in order to get my vector direction. So what I'm going to do now, because it is cluttered, I'm going to take these off, and that way, I just have my diagram. So this is what you're going to want to this is what you're going to want to kind of reduce it to. Now what I'm going to do is I'm going to add the directions or the orientations of my vectors. Now, I'm going to look back at what we drew earlier. So I'm going to start by putting in my velocity of B. So I'm going to go back over here. I'm going to change my layer. I have it on object 2, and I'm going to create a line, and I'm just going to go randomly out here. And I just want to do my object snaps to be perpendicular to link number 2. Okay, so that's the orientation of the line. Now what I want to do is I want to look at the magnitude of the velocity of B. Okay, my velocity of B is 7.853, and the dimensions that I'm working with on my drawing are like 4 inches and such. So I'm going to keep this at a 1-to-1 scale. So I'm going to draw this at 7.853. So going back to AutoCAD, What I'm going to do is I'm going to move this. I know that I'm going to just go back one more time. I know that this is going to go up and to the left because I'm in a counterclockwise direction here. I'm sorry, clockwise direction. So I know that's going to go up and to the left. So I am going to move my line endpoint of it to the center of B there. Okay, so it's right on B because that's where this is located. And now I'm going to use my circle center radius at the center of B there. I want this radius to be equal to 7.853. Okay, 7.853. Okay, and that's big. All right, so I need to then extend my line to that radius. Okay. Now I can get rid of that radius because I just needed it for construction. And now I'm going to add the lines for the direction of my vector going up and to the left. Okay. And this is vector B. It is a little smaller. That's okay. You know what? I would suggest you're probably gonna have to take 2 screenshots. So I'm going to copy or make your stuff larger. And I'm going to, this is going to be velocity of B, and I'm going to scale this to be bigger, just so that I can see it. So you might have to play around a little bit with the directions here. I don't think I'm regretting it, but maybe I am regretting it. I don't like it. So I'm gonna undo, 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 undo. What we're gonna do is instead of 1 to 1, because this is really big compared to it, I thought it would be a little bit closer. I am going to instead divide this number by 10. So I am going to draw, I'm going to do a new radius to be 0.7853 radius of that circle. So this is shorter. So sorry, but you know what? It's okay. So I'm going to do another circle center radius. Make sure that your center is at the center of B there. And now this radius, instead of 7.853, I'm going to do 0.7853. So again, dividing that number by 10, hit enter. Yeah, that's better. That way I can use the same fonts, sizes, and such for everything. So we're going to show that going up into the left. And then I'm going to add my lines for my arrowheads here and here. And then I will copy B out here and relabel this velocity of B. Okay. That's there. All right. Sorry about that little detour, but sometimes that happens, right? All right. So my velocity of B is perpendicular to link number 2 in the direction of rotation. The rotation, as we know, is clockwise at 100 RPMs. Okay. Any questions on that one and the scaling? So we divided by 10. So we'll have to keep that in mind so that when we report out our final answer, it will, reflect the correct units. Okay, so now that took care of my velocity of B. Let's put in the direction for C relative to B, which is perpendicular to link number 3. So going back to AutoCAD, changing my layer to object 3, and I'm just simply going to create a line that is perpendicular to that link number 3, okay? And then I'm just going to copy this from here to simply represent C relative to B. So that's the velocity vector orientation for C relative to B. Then my last one is going to be the velocity of link number 4 or point C. And in the direction that we're going right now, we're anticipating this going straight up. So we are going to show our line from the center of C, and we just want it to be, we put on ortho, just want it to be up right about there. Okay, just to represent that, and you can get rid of that construction line if you have it. And this is going to represent the line of action of the velocity of c. Okay. And again, no arrowheads on the last two because we don't know how long they're going to be. So any questions so far? Not a bad idea to do a quick save because we want to have a screenshot with these orientations of not only the kinematic diagram, but also the labels and orientations of the vectors. Okay, so now we are ready to do our vector or relative velocity vector equation, which is this right here. I'm going to start by, and I do like doing this, I'm going to start by putting my vector equation in place first. So velocity of c, I'm going to make this a little longer, is equal to the velocity of b plus vectorially velocity of c relative to b. Okay, so that's our base equation. I like having that handy and on the screen first. And then I'm going to go back to my object line layer, and I'm going to create my origin. So I'm going to put it here, make sure that they're horizontal and vertical lines so that it looks like an obvious origin. And now what I'm going to do is I'm going to start where I know the most information. As we know the magnitude and direction of velocity of v. So I'm going to copy my velocity b vector, and I'm going to start its tail at the intersection of my origin. Right there. Okay, velocity of b. Then on the tip of b, I'm going to add the direction, the orientation of the velocity of c relative to b. So I'm going to finish out the right-hand side here. So I'm going to do a copy. And I'm going to select this. I'm going to use nearest. And I'm going to go on the endpoint here. Okay. Now I've got some things I got to move around. I'm going to put b over here. There. And we'll just kind of keep that there. Okay. And that takes care of my right-hand side of the equation. Okay. Now I'm going to cross over the equal sign, which means I'm going back to the origin, and I'm going to place velocity of c. So the velocity of c, its tail is going to start at the origin, and it is going to point to whatever the intersection is for the other side of my equation. So you'll notice that I have an intersection right there. So that means I can get rid of the things that are sneaking out on either side. So I'm going to move my designation here. This is going to be velocity of c. And this is going to be the velocity of c relative to b. Okay. Now, arrowheads. Let me move this a little closer so we can zoom in and see the equation. On the right-hand side, I've got the velocity of b. That's right here. On the tip of b, I'm going to start the tail of velocity c relative to b. So this is the tail here. And the tip then would be going up and to the right. So I am going to draw my line right here for the arrowhead of velocity of c relative to b. Okay. Now, that takes care of the right-hand side of my equation. I cross over, and my tail of velocity of c is going to start at the origin, and its tip is going to be going straight up, and it's going to be at the endpoint of the velocity of c relative to b. So this is going to be pointing up, which is exactly the way we anticipated this to go. Okay. So now the only thing left is to add its magnitude. So I'm going to do a linear dimension because it's going straight up. You could do aligned as well. And you'll notice that my value comes out to be 0.742. Okay. Now, before we leave here and we go to kind of finish up the problem, what you see right here is the screenshot that you want to take to hand in as the CAD work for problem 623. Okay. You can either do it in two separate screenshots or you can put it in one as long as they're large enough so that when you add them to the assignment, they're large enough for me to see. Okay. So now what this means is remember, we scaled the length of velocity B to be 1/10. So we divided by 10 to get the length. So now this value for the velocity of C is going to be multiplied by 10. So our final answer is actually going to be 7.424. Okay, 7.424. So I'm going to go back underneath here. Step number 4, velocity of C is equal to 7.424 inches per second. Because remember, this was our actual answer. It was too big to draw, so we divided by 10. Okay, so now when we measured our value over here, it was 0.7424. That means that we're multiplying it by 10 and the magnitude is going to be 7.424. So make sure that when you're scaling anything that you do your multiples back and forth. And this is going to be going straight up. Okay, so we need both magnitude and direction. And this would be your final answer. Now, handing in wise, the work that we did right here is what you want to hand in. The only thing that's optional here is I like to draw out our diagram before I go to CAD. If you don't do this, that's okay. That's okay. As long as you start here and show me this work. Okay. And then you add on the screenshot to show the CAD work to verify those numbers. All right. Now, I guess we should compare to our final answer. Let's go back to our final answer. And you're going to notice that, oh, sure enough, look at that. Exactly 7.424 is the answer for 624 for the velocity of C. So before we, kind of close it up here, are there any questions on 623? Okay, I'm not hearing anything. Logan said
I feel pretty
no.
good.
All right, Lars says good. Okay, well then what I'm going to do is I'm going to stop the recording here.